Welcome. In this lecture, I want to go through the if-then kinds of statements, or the kind of implies symbol. So let's get started. So the notation we're going to look at this time is that if I write, if I write P, and then I put this symbol, so implies, and then we have Q. Right, so what is the meaning of this? So the meaning of this is, so we could say this as saying that P implies Q. Okay, or another kind of way of saying what this means is if. So if P then Q. Okay, and so these can be used, so something to be aware of. So the first thing to kind of be aware of is that this can be used in a statement with no promise of it's actually being true. Okay, so can be used in a statement with no promise of the statement being true or false. So here's kind of some examples, right? So for example, I could write a statement like, prove or disprove that. So prove or disprove that P is even implies P squared is odd, right? So looking at that statement, you can tell, hopefully, or eventually you'd be able to tell, like a statement like that is not, it's not actually true, like this statement. So it's a false statement, but sometimes we're going to say it in order for, as like an investigation, like, is this a true statement, or suppose this were true, or something like that. Okay, or here's kind of a great example. So soon you might see statements like, suppose for the sake of contradiction that if I can walk, then I can fly. Right? So I might say something, this, right, this is not a true statement, but this is one of these circumstances, like I was saying, like before, where you're stating it as like a hypothetical, like if this were a true statement, then all these other things would be true. Okay, so that's, you need to be able to make statements that are false like that in order to structure your logical arguments. So it's okay to kind of look at statements like that. Okay, so okay, the other part of this is, so perhaps most commonly it implies, right, so even though we can use this for like false statements, right, I would say that perhaps most commonly right, it implies I'm going to kind of do this thing so that it's clear that this is something is separate. So it implies right, Q is true since P is. So Q is true since P is. So Q, I'm trying to see how I did that there. So I wrote it like this. So Q is true since P is, oops, P was in orange, since P is. And actually here it's showing up like this. Okay, so here's some examples. So here's one, which is that n being even implies, so n even implies that n equals 2k for some k in the integers, okay? And usually in a statement like this, you'd want to put in, right, by definition, right, to say why. Okay, so here's the next part. Here's another one. So we could do n even implies that we have, oops, this is, the last one was n even. I read the wrong part of the paper. Okay, let's clean that up for ourselves. Okay, so if we have that x, y, and z are real numbers, so if I have the x, we can do this. I know you believe in me. Okay, so x, y, and z are real numbers. X is greater than y, and z is greater than 0, that this implies that xc is greater than xy. Okay, and this here is by an axiom. You know, I'm trying to set a good example by always stating how we know. Okay, and then another kind would be, so here's one more example, which is that if we have f of x equals x squared is continuous and defined on on 0, 1, okay, and right, and we also have that f of 0 equals 0, f of 1 equals 1, and 0 is less than or equal to 1/2 is less than or equal to 1, then this implies that f of c is equal to 1/2 for some c in this interval, okay? And this would be by, so we've done something that's by definition, something that's by an axiom, and this would be by a theorem, so this is by the mean value theorem, right? So those are kind of several reasons that we can have. Actually, I want this to be consistent so that you can, it stands out properly, so let's just do this in the same, so this is by definition. I like the structural similarity, so it's easiest to see what's going on there. So it could be by definition, by axiom, by theorem. So you should have a reason, but you will have, like, in the meat of your proofs, like in the structure, as you go through, you're going to have these if-then statements, and there's going to be a reason why they hold. They can hold by definition. They can hold by axiom. They can hold by a theorem. Okay? And you're going to see lots more examples over time. But let's look at some other forms. This is the last thing I want to highlight here. So other forms. Okay, so one of them would be Q if P. Okay, so that's one other form. There's a lot of different forms. And so P only if Q. So P only if Q. Okay, so these are all have the same logical structure to them. They're just kind of different ways of writing the same thing. And there'll be circumstances where you'll want to actually use the different ways of writing the same thing. But more commonly, actually, you're going to see other people using different ways to write the same thing, and you want to know that they're actually talking about the same thing. Okay, the one other final remark before I kind of go through and recap a little bit. This is shorthand. You're going to see professors using it on the board. You should use it in your scratch work. It's like nice and fast and makes things easier. It doesn't go in formal proofs. So when you're turning in your papers, we don't want to see these logic symbols. It's just the culture of mathematics, which we're trying to teach you, and part of that is that you write things in complete sentences. But the other side of that, because also a lot of students worry if English isn't their first language. The other side of that is that a lot of these words are actually logic words. And so if you learn the logic words, you're really almost writing things symbolically. You aren't really using English, you're using this like logic language, okay? But we don't put that in proofs. Like we don't put this one in something that we turn in. We might put it on the board to save ourselves time. So the other things kind of to go through. One is that sometimes we're going to say a statement that isn't necessarily true, that has an if-then in it. And there's still logic in that. So you might need to disprove it. It might be like, suppose this were true, and then these things would happen, and that would reach a problem. It has several different forms that you might see it in, so it's good to know those. So we've seen this, we've seen this, we've seen this, we've seen this, we've seen this. So we've seen five, 1, 2, 3, we've seen 5 different ways that it might show up. They all are like logically the same. And there are reasons that you're going to see in proofs that these might hold. So they might hold because of a definition, because of an axiom, because of a theorem. Okay, so I hope that was helpful, and I will see you in the next lecture.